Hello everyone, welcome to this next video on field theory. In this video, we are going to talk about finite fields and we shall see several examples of the finite fields, right? So let us start with finite fields. What are these? A field F is a finite field if the set F is a finite set. What do you mean by finite set? A set which contains finite number of elements, the number of elements which you can count, right? So this is the simplest definition of finite field. So now let us look at several examples. What I have done here is I have collected various sets along with different field operations, and so that you have to tell whether these algebraic structures with the given operations are form a field. Moreover, if they form a field, do they form finite field? So this is the task. I may suggest that you pause the video here, you note down these sets along with the operations, and you think whether they are field or not, why they are field and why not they are field. Just note it down. These are first 4 examples. Next examples are these, and these are the examples, right? Once you are done, resume watching the video and then you can see if your reasoning is correct or not, right? So let us get started. The first option is this. You are given set of integers and the operations given to you are usual addition and multiplication, right? So now we just have to check that whether this forms a field or not. Clearly this is not a field. If this is not a field, this is also not a finite field. The reason for this is that why this is not a field, because here the multiplicative inverses does not exist. For example, if you have some number 2, which is the integer obviously, so we do not have multiplicative inverse which is 1 by 2 into the set of integers. Therefore, this is not a field, right? Let us look at next example. The set of rational numbers along with the usual addition and multiplication. Yes, it is a field. Moreover, does this set is finite? No, it is not finite because it contains infinitely many numbers, right? So this is not a finite field. This is a field but not a finite field. I have a separate video on this. If you are having any doubt, you can watch that. Next example is the set of real numbers. The given operations are the usual addition and multiplication. Yes, it is a field. Moreover, it is and the set of reals is an infinite set, right? Therefore, this is not a finite field. So this is not a finite field. This is not a finite field. Yes. So the next example is non-negative real numbers. This is the notation. The operations given are usual addition and multiplication. Now this is not a field. The reason for this is that it does not contain additive inverses. For example, you have some number 2 by 3 which is in this set, right? This is a non-negative real number, but the negative of this, that is the additive inverse minus 2 by 3, does not belongs to the same set. Therefore, this is not closed under additive inverses. Therefore, this is not a field. If this is not a field, you cannot say whether it is finite or infinite. The next example is the set of complex numbers under the operations of usual addition and multiplication, right? Yes, this is a field. Moreover, this is an infinite field. It is not a finite field because the set of complex numbers is infinite. Let us now move on to next example. It is the set of all 3 cross 3 matrices M3R with entries in real numbers. That means you have some matrices of this form A, B, C, D, E, F, G, H, I of this form, right? And this A, B, C, these all are some real numbers, right? And here the operations given to you are matrix addition and matrix multiplication. We usually the same as you do in matrix algebra, right? So now, is this a field? No, it is not a field. So we cannot talk about finite or infinite. The reason why this is not a field, because we know that matrix multiplication is not commutative. Therefore, this is not a field. Right? Next example is all 3 cross 3 invertible matrices GL3 are, where what is this notation? This notation suggests that it is a general linear, it is basically a group, right? So this is a general linear group whose entries are in R with order 3, right? So they are saying the speciality of this group is that it contains all the invertible matrices. That means the determinant of all the matrices given here is non-zero, right? So we can say that now is this together with the operations of matrix addition and matrix multiplication is a field or not? Again, it is not a field. Why? With the same reason, because matrix multiplication is not commutative. Even if you find the inverses and identity elements, there is no commutativity among matrices. There are several examples for that, right? Next, the group of this group ZP, which is the operations given here are addition modulo P and multiplication modulo P. With these are the notation for this symbol. Now this set, what is this set? This is the set consisting of equivalent classes 0 bar, 1 bar, 2 bar and so on up to P minus 1 bar. That is, you are having classes with one number less than this given number P, where in this case this P is prime. So, what is each class? This means, it means that, for example, I am taking the class 2, right? So it contains all numbers which when divided by P leaves a remainder of 2. Right? So all those integers, this Z is representing integers. So all those integers which when you divide by P leaves a remainder 2 comes under this class. Similarly, I have 0 bar, 1 bar, 2 bar up to P minus 1 bar, right? So this is a set. And the operations given to you are addition modulo P and multiplication modulo P. In addition modulo P, we add these numbers and when we divide by P, whatever is the remainder is our answer. For multiplication, you multiply two elements, and then you divide by P, and whatever is the remainder is your answer. So this is a field. Moreover, the set contains a finite number of elements, right? Therefore, this is a finite field. So we got one example of finite field, right? So this is our example. You should know this one. This is a finite field, right? If somebody is interested in how we obtained this, I have a video for that. You can find the link for the video in the description. The next example is Z divided by NZ. What is this? Where N is the composite number. What is a composite number? a number of this form where you can write it as a product of primes. So for example, you have 6, so you can write 6 as 3 into 2 into 1, right? So this is a composite number, and we are given the same operations, addition modulo n this time and multiplication modulo n this time. Now this is not a field. Why this is so? Why this is not a field? Because it does not contain multiplicative inverses. I highly recommend you to solve this example. Why? The reason is that because you'll clearly see once you draw the tables, addition modulo n and multiplication modulo n tables, then you will be able to see why the multiplicative inverses are not available. We cannot just simply visualize this. We have to perform and create tables, and then we can visualize the things, right? For that, what you have to do, you just have to list all the elements of this set. For example, you take n to be 4, then you'll be looking at this set, right? So what are the elements in this? It would be 0, 1, 2, 3, right? And so the addition modulo 4 would be 0, 1, 2, 3, and here it would be 0, 1, 2, 3. Then you complete this table. Similarly, for multiplication modulo 4, it would be, the elements would be only 1, 2 and 3. We exclude 0 from the set. So you just complete the tables and just look for all the properties. You will find the multiplicative identities, additive identities, but we do not obtain this multiplicative inverse, right? And the last example in this for this video is polynomials qx, where q, what is this q? Q is the set of rational numbers in x with coefficients in the set of rational numbers, right? And the operations here are polynomial addition. What does that mean? If we take any two polynomials, say I have x plus 2x as one polynomial, 2x square, and another polynomial as 1 plus 2x, say, right? So what would be the addition? Their addition would be, it would be 1 is added to the constant, and then the coefficients of x are added, so it would be 1 plus 2, that would be 3x, and then the coefficients of x square are added, so here there is no term of x square, so it would be 0 plus 2, so that would be 2x square. This is the usual polynomial addition. Similarly, the polynomial multiplication is what? We have two polynomials, 2 into x square, right? Another polynomial is this. How do we multiply? We multiply each term separately, so x into 1, that would be x, plus 2x square, this term into this term, right? Then this term into this term, that would be 2x square, plus this term into this term, that would be 4x cubed, right? So this is the usual notations and the algebra of polynomials, which we are doing since our previous classes. This is also not a field. Why? Because here it also you do not find the inverses, right? The multiplicative inverses. For example, if you have polynomial of the sort f of x is equal to x, where the coefficients are in rational numbers, right? Where this fx belongs to this set of rational numbers, then its inverse, what would be that? The inverse of f of x, that would simply be 1 by x, which does not belongs to this set, right? So this is not a field. So from here we just obtain one single example of finite field. What is that? It is this set together with these operations, right? That is it for this video. Thank you for watching.